day of 1.8. We have 2 types of problems to do. And then tomorrow, remember, is going to be a day of working on all 3 days. I will be doing one example at the beginning of class, which is long division using polynomials. We did synthetic division last week, and I was supposed to do long division. I just couldn't fit it in, so I'm going to do one example tomorrow. And then when it comes up again later, of course, I'll go over it again. But I just want to get that in. It's not on this next test or anything, but I want to do it when we're close to synthetic division. So tomorrow, bring all 3 days' work. That would be a great day to have your laptop and go back over your quiz and ask me, why did I get this wrong, if you got anything wrong, because you'll be able to see tomorrow how you did. Also on your progress thing on AP Classroom, that's already closed, so you should be able to see how you did on that. Use tomorrow to, like, tie up loose ends. Ask, I never understood how to do this problem, or whatever. Remember, tomorrow I'm just at your beck and call, like whatever you guys need. So bring stuff to do and for this class, and then we'll have a homework check at the very end of class, okay? All right, any questions for me? Okay, so I'm not going to go deep into transformations of functions right now. We have one more section, technically 1.9, to do, and then we are actually going to do, I think it's like 1 day of going over all different types of transformations of functions, which is really a review of stuff that you learned in Algebra 2, hopefully, but of course I'll be reviewing it. And this is going into it again pretty quickly, and I'm not going to go through all of it. I just want to talk about transformations because we are technically transforming these rational functions here, but we're not really doing too many of these types. So I just want you guys to know transformations means changes to the graph. It's like an umbrella term. And then we have like translations, we have dilations, we have reflections, probably more I can't think of, which just basically means how the graph moves. And the first 4 are your translations, left, right, up, and down. I just got Hakeem, Miss McClure, what's her name? She said, hey, sorry, can you send him now to testing? He is on our list. Thanks. That's what she just sent me at 8:23. She must have not realized it. I'm just saying what it says. Don't be doing it. I'm sorry, sweetie. Sorry. So up and down is the number all the way to the left, all the way to the right, and a number in parentheses is your left or right. And we'll talk more about that later. But just understand, I'm going to kind of relate back to that with these last rational functions. So these are going to be your favorite rational functions. If you had to pick which day of rational functions did I like, you'll say today's, okay? Because these are really easy, fast, quick to graph. Because if you remember, we started really difficult, where we had to pull out VAs, HAs, holes, x-intercepts, y-intercepts, symmetry. We did some sign change charts. We've done so much with them. These are super quick. They're very, very simple. These are considered, bye, sweetie. These are considered rational functions. It's a fraction. And that number on top, if you notice, there's no x's. Those are monomials, like one single number. But it still is a part of the polynomial family. And it's a fraction. So these are considered rational functions. There's no factoring. There's no holes. There is a VA and there is an HA. So we talk a lot in algebra about parent functions, also known as power functions. They're like all the basic graphs. And the basic graph for these is just 1 over x, okay? Then we start putting numbers in the bottom and up top. Maybe we change it. Maybe we put a negative there, a number out to the right. But just a quick sketch of the graph. You just have 2 branches in quadrants 1 and quadrant 3. So that's just the most basic graph you could have, okay? So what happens when we do throw these numbers in? So we're going to identify a VA, an HA, and we're going to make an XY chart with just 2 X values. That's it, okay? And the VA and the HA is just pulling right out of this function. We'll graph those asymptotes, then we'll pick 2 good numbers, one to the right and one to the left of our VA, kind of similar to what we've been doing. So we're just not making it specific, like what is the x-intercept, what is the y-intercept. These are really basic graphs. So the VA shouldn't be confusing to you. We still get that from our denominator. We set our denominator equal to 0 and we solve it, right? So x equals -2. And in this example, it's really easy to explain what our HA is, because technically, there's x to the 0 on top, right? No 0 is what that means, which also simplifies down to 1. Hi, I didn't look at you when you knew that name. Okay, I'll turn down him a little bit. Okay, you could assume that that's x to the 0, right? And anytime it's smaller on top than the bottom, remember, we have to know those HAs. It's y equals 0. Anytime it's smaller on top than the bottom, it's y equals 0. So let's just go ahead and sketch those two asymptotes. X is -2, y is 0. And make this super simple. Pick a number to the right, pick a number to the left. I always like to use 0, which is my y-intercept. So as long as my y-axis is not an asymptote, there is going to be a point somewhere on the y-axis. So I just think 0 is a super easy number to plug in. Does it have to be 0? Nope. You can pick any number to the right and any number to the left. So maybe 0 and then -3. But it really doesn't matter. These are pure sketches. We're just figuring out what little quadrant we're in. Okay, so when I plug in a 0, I get 1/2. And when I plug in -3, I get -1. Okay, so 0, 1/2. And that tells me I'm going to have one of my branches in this quadrant. It does not have to be perfect. We don't need to make a whole bunch of points. It's very, very rough, as I keep saying. And then -3, -1, and that graph is done. Done, done, done. Now, why did I even bring up the transformations part of that? Why is that linked to it? Because that number in the denominator is a horizontal transformation. Think about what it did. From our parent function, which was like the traditional x and y axis, it shifted all the points to the left too. And there was no up or down, right? Our horizontal asymptote stayed right where it was. We didn't move that up or down. So let's look at the next example where, again, we'll plot our VA. That's always that number in the denominator. Anything the x can't be that doesn't cancel with the numerator. And the horizontal asymptote on these actually comes from that +3. Because remember, the number over here, all the way to the right, shifts your graph up and down. So these are a little different where we're not really looking at, well, it's kind of like saying my asymptote is y equals 0, just like it was here, and then add 3 to it. So it's y equals 3. So that number out to the right is simply our asymptote. It's going to shift all of our points left 1, up 3, which just shifts our axes. And then by doing that, it moves all the points. Okay, so x is -1, y is 3, left 1, up 3. Quick xy, make this easy. Yes, I'll use 0, because that's an easy number. And then any number to the left of -1. Doesn't have to be -2, any number. If you want to match your key to mine, like when you're checking, I'm pretty easy to predict. I always pick the one number to the left. So when I plug a 0 in here, I get 2/1, which is 2, and 2 plus 3 is 5. -2 plus 1 is -1, so 2 divided by -1 is -2, plus 3 is 1. Just be careful plugging in. Where am I? 0, 5, and -2, 1. So you can see, right, with just those 2 points, we know exactly where our branches are going to be. Okay? And are pretty repetitive. VA, x equals 3. HA, y equals 2. Now notice the number on top has a negative. We didn't really go into it, but a negative on top just like with a parabola with a negative in front of the equal sign, flips your graph. So we're going to go from branches in quadrants 1 and 3 to quadrant 2 and 4. You'll see. So x equals positive 3 and y equals 2. Yep, I'm going to use 0 and 4. So when I plug in 0, I get 1/3, right? So -1 over -3 is positive 1/3. So 1 divided by 3, and then plus 2. And I get 2.3. I can change it to a fraction if I want. But for graphs like this where we're not being precise, 2.3 is just fine, okay? And then -1 over -7. So, I'm sorry, when I plug a 4 in here, I get 1. So -1 over 1 is -1, plus 2 is 1. So 0, 2.3, right here, looks about right. And then 4, 1. So as predicted, our branches flipped. By having that top number be a negative. It just happened naturally. And don't overthink that denominator. Don't forget what you already know. We get a VA from our denominator. Any x's in our denominator that don't cancel with our numerator. Set it equal to 0 and solve. Add 4, divide by 2. It's still x equals 2, right? The only time I can't choose 0 for an x value is when. Because it could happen. When can I not use x as 0? When what equals 0? When the asymptote does. Yeah. So if you have an asymptote on the x-axis, which is y equals 0, so the horizontal asymptote, if there was an asymptote there, I couldn't choose 0, right? Because it's not, you can't have a point on an asymptote. So that's all I mean by can I pick 0. That's all I mean. So that's going to be over here, and then I want a number to the right of that, like 3 maybe. So 0 in my denominator gives me -1/4 minus 3. I have -13/4 written on my paper, but what is that? 13 divided by 4 is 3.25. So that's negative, I'm going to put it here, -3.25. And then when I plug in a 3, that's 6 minus 4 is 2, 1/2. So I'm putting in my calculator fast, 0.5 minus 3. We just have so much work to do all the time that I think it helps to try and find those shortcuts. Instead of taking the time to type in 1/2, use 0.5, okay? So to the right 3, let me see if I get this right, down 2.5, it gets me like right here. And then 0, negative. So it's kind of a weird looking graph, but it's just because our asymptotes are in kind of weird places. So you can kind of make some predictions with these to help know if you did this right, because that's kind of what I was looking at. You know if that top number is positive, we should be in quadrants 1 and 3, our modified quadrants, from our asymptotes. And if the top number is negative, we should be in the modified 2 and 4. But these should be quick, easy, no stress. Are we good on this example? Yes. Which number? Okay, so do you agree with me? Maybe I made a mistake. I'll put a 3 in there. 2 times 3 is 6, right? 6 minus 4 is 2. So that's just 1/2. and then minus 3. So I just put 0.5 minus 3 in my calculator. Tell me exactly what, because there are sometimes that the way you put it in the calculator makes a difference. I'm going to guess, Aaliyah. Tell me if I'm doing this the way you did it. Did you do 1 divided by 2 times, did you type it in just like this? 1 divided by 2 parentheses maybe? 3. Like this? And then minus 3? Okay. So I'm glad she said this. Look at that. Like, it's exactly what we say, right? It's 1 over 2 times 3 minus 4 minus 3. Your calculator is going to do exactly what that says. Your calculator is going to do 1 divided by 6 minus 4, then minus 3, which is not going to give the same answer as mine. Sometimes you need to do a little, if you wanted to type it in your calculator left to right, this is what you would have to do. 1 divided by, in parentheses, 2 parentheses minus 4, close the parentheses. So if there's an operation to be performed in the denominator, you have to kind of separate it. Say, do this before we go on to anything else. Okay? So I should get 0.5 when I do that, and then minus 3. So just understand, that's why sometimes I don't want to type everything in my calculator. I might do a little bit of math in my head. It saves me, 2 times 3 is 6, 6 times 4 is 2. It saves me having to type in parentheses and stuff, or from making any mistakes with my order of operations. Does that make sense? Yeah, I'm glad you brought it up, though, because we tend to want to, I see it all the time. And I always say, take control of the order of operations. Like, always, like, sometimes I will even type it in as, let's say I didn't want to do any of it in my head. I might do 2 times 3 minus 4. I might just put that in and be like, okay, so that's 1 divided by 2, and then minus 3. You know what I mean? So find like at least some of it that you don't type it all in, so you don't make that mistake. Okay? Anybody else before we go on to our second of 2 types of problems? Okay, so we've already done problems like this before, somewhat. These are where you're solving polynomial and rational inequalities. What we're looking for is where the graph is above the x-axis, hence greater than or equal to 0, or greater than 0, or below the x-axis, which is less than 0. This is our sign charts, okay? They're not new to us, so hopefully this is just practice. Let me just go over it again, okay? So what we're asking here is, where is this graph greater than or equal to 0? In other words, above the x-axis. That's what that means, okay? And they gave us a graph on this one. So if I were going to look at this graph, I could roughly say, well, right here, right? Anything above the x-axis. So these 2 pieces, right? How do I write that out? Well, you first have to kind of look at some pieces of the graph. Like, where are these asymptotes? There is an asymptote at -3, and this one is really hard to see. If you go by the graph, it actually looks like it's touching 3. But I know that it's a 3 because I know a little something about vertical asymptotes, and that is anything that in my denominator has an x that doesn't cancel with the numerator is a vertical asymptote. So I'm pretty sure that -3 and 3 are vertical asymptotes. And the numerator is 1, denominator is 2, so I have a horizontal asymptote of 0. And remember, on these 3-part graphs, we can cross that horizontal asymptote in the middle. So that's important. You really have to know where that stuff is. And then now by looking at the graph, I can name these parts. So where am I above the graph? I'm above the x-axis, here and here. Now notice it said greater than or equal to, okay? So why I'm bringing that up is how to know if we're going to use brackets or parentheses. It's really important. So we always use parentheses for infinity symbols, right? We'll never use brackets for those. And we would always use parentheses at a asymptote or a hole, but there's no holes here, okay? So think about this. Where am I going to be above the graph here? This would be starting at -3, but because it's an asymptote, I'm not including it, right? All the way to what number do I cross over from 0 to negative? Right here at 2. Would I put a bracket on the 2? Yes. Because of the equal to sign. It said, where are you greater than or equal to? If the equal to sign weren't there, tiny little symbol, you would have parentheses. Okay? But it wants anything that also is 0, and that is 2, 0 right there. And you should know that, because look at your numerator. Set x minus 2 equal to 0 and solve. You get 2, that's a 0. 2, 0 is a point. Okay? And you could put a union sign, you could put a parentheses, doesn't matter. And then again, from positive 3, that's an asymptote. And because of this asymptote right here, y equals 0, I'm going to stay above the graph forever. Okay? So there's one with the graph given to us. Okay? Let's do a polynomial one. This is just a polynomial, not a rational expression, because it doesn't have a fraction, right? There's no fraction. So this is just kind of, we've done these before to get us ready for the other ones down here. What you have to do is find those important x values, okay? Important x values are vertical asymptotes. We don't have those. Holes, we don't have those. We do have zeros, though. X-intercepts, we have 3 of them, right? These are the 3 important zeros where things happen at the x-axis, right? That's where stuff happens. So we do our little sign chart, least to greatest, and we have to pick numbers in those intervals. Anything that you want. I always try and use 0 whenever I can, right? So I'm going to use 0, which is to the left of 1. Going to have to use a decimal or a fraction in here, but you could use 1.25, 1.75, anything, 1.3, whatever. 3 and 5. Now, what we're looking for here is where we are less than or equal to 0. But let's just plug it in first, okay? And guys, use this big screen. Don't make this more work than it has to be. So what I would do here is I would do 0. Maybe I wouldn't do all of this work, but let me just show you how you could show a lot of work. I'm just putting them all in there. So I put all 3 numbers, 0 minus 1, 0 minus 2, 0 minus 4. I can see all 3 of them. And then what would I do with those 3 numbers? What do I do with them? Nobody knows? There are like 6 of you in this classroom that are ranked 1 in the 10th grade. So you better know what I do with these 3 numbers. What does it mean when I have this number, and this number? What do those parentheses mean? Multiply. They're right there. -1 times -2 times -4. If you needed to put in the calculator. I don't know if you would. And I get -8. Is -8 less than or equal to 0? Yes, that's true. So I've got one piece of the x-axis where I know I'm going to be below the x-axis. I'm not graphing, I'm just doing it using this. And then 1.5 minus 1, 1.5 minus 2, 1.5 minus 4. They're all right there. There's no chance of me making a mistake. 0.5 times -0.5 times -2.5, and I get 0.625. Is that less than or equal to 0? Nope. And we would keep on going. We get -2 when I plug a 3 in. True. That's less than or equal to 0. And when I plug 5 in, I get 12. That's false. So I have 2 places on the x-axis where I'm below. So picture it. Whatever the graph is, those parts of the graph would be below the x-axis, hence less than or equal to 0. Okay? So that's -infinity. Always use parentheses for infinity symbols. Up to 1. Bracket or parentheses? It's less than or equal to. Remember, the only time we have to worry about parentheses is infinity symbols. I think we know that. And asymptotes or holes. We're not going to have any holes in this, and there's certainly no asymptotes because there is no x's in the denominator. So these are x-intercepts. 1, we touch the graph at 1, we touch the graph at 2, we touch the graph at 4. And then we also have from 2 to 4. Also, brackets. Okay? So that is where our graph would be below the x-axis, less than or equal to 0. Okay? Let's do one like that, skip to C, but make it a rational expression, so there's something in the denominator. It's still an important x value. Remember, anything that's a 0, okay, that's 3. Anything that's a vertical asymptote, -1, are going to go on our sign chart. But we will be really careful after we plug in. We'll be really careful with parentheses or brackets. So what did I use here? I used -2, I used 0, I used 4. Okay, so again, use the calculator screen to your advantage. Don't make mistakes here. So -2 minus 3, there's my numerator. -2 plus 1, 1, there's my denominator. Then I'm going to what? Am I multiplying these two numbers? What am I doing with them? Dividing. Yeah, I got -5 on top. I got -1 on the bottom. I don't need to really put that in my calculator. That would be 5. Is 5 greater than 0? Yes, it's true. -3 divided by 1 is -3. Is that greater than 0? Nope. And when I do this one, I get 1/5. Is 1/5 greater than 0? Yes. Okay, so from -infinity up to -1, and then from 3 to infinity. So let's be careful. -infinity, you got that, up to -1. -1 came from my denominator. That makes it a vertical asymptote. That's why I put parentheses. You can't have a point. Nothing touches the asymptote, so it can't be included. All the way up to it. Then, from 3 to infinity. Now be careful on the 3 as well. We want numbers that are greater than. So at 3, 3 is a what? What is 3 actually on the graph? If I made you guys graph this, 3 would be an x-intercept. And that means it's not above 0. It's at 0. So it's greater than. If it said equal to, it would be a bracket. Because it doesn't say equal to, it's a parentheses. So they're all parentheses in that case. You really have, this is really making you see if you understand what happens on the graph. Okay? So understand at x is 3, you probably have a branch, I don't know, like this. So it's not touching, it's above 3, it's not on 3. Okay? All right. Now, there's one more to do, and this one I saved for last because it's got an extra step in it. I have no idea why she did them in reverse. But I want you guys to notice that there's a 2 here. So we have to do a little bit of fancy algebra. This is our last example. I need to bring that 2 over because when you do these, we have to make sure the right-hand side is 0. Okay? So if it's not, we have to bring that number over. So I'm going to subtract 2. And I need to subtract them. And I can't even use my calculator on this. I need them to have a common denominator to be able to subtract them. And right now they don't have a common denominator. Easy to determine what the common denominator would be. We want them both to have x minus 3. It's easy to change a 1 to an x minus 3. So I'm going to be multiplying this guy, the denominator, by x minus 3. And I'm allowed to do that as long as I do the same thing to the numerator. Okay? So I would have x plus 1 over x minus 3. And I'm just going to put a plus here because I'm going to take care of this -2 when I distribute. And I will end up with a negative here, so I could have left it, but I wasn't sure. So -2 times x is -2x. -2 times -3 is +6. Now they have the same denominator. And I'm just going to put it together under 1 over 1 denominator. So x minus 3 and then just combine like terms. I have x minus 2x, which is negative x, and 1 plus 6 is 7. Or I could have written 7 minus x. And that would be less than or equal to 0. Okay? So, same steps. My important x values. Of course, that denominator of 3, that's an asymptote, right? No brackets on that one. And I set this equal to 0. Subtract 7, divide by negative 1. We get 7. So those are my two numbers. So remember, I like to use 0. I thought I was going to pick 2. Pick 0. I like 0. Remember, any number in there. 4 and 8. So you're plugging the numbers in. So when I plug a 0 in, I'm just going to tell you get negative 7/3. So is that less than or equal to 0? Yep. Negative 7/3 is less than or equal to 0. And then I get 3. Wait, that's not right. Where am I? When I plug in 4, I think I get 3. Must get 3. Is 3 less than or equal to 0? No. Sorry, I can't read my writing. And then when I plug 8 in, I get negative 1/5. And that, of course, is less than or equal to 0. Okay. So where am I less than or equal to 0? From negative infinity up to 3, and then from 7 to infinity. Now don't forget, 3 is an asymptote. So here's my answer. From negative infinity, right, that's all of this, all the way up to 3. Since 3 came from my denominator, I have to use parentheses. Then from 7 to infinity. 7, perfectly fine. And that would be our final answer. So you can probably already see where some of the questions can come in. It's not really doing this math anymore, even though it's annoying. It's just plugging into your calculator. It's the brackets versus parentheses. And that gets confusing, okay? So let's practice using homework. Question before we go on to the homework? Okay. So, practice set 3, a 23, so remember, finish working on this for the rest of the period. Tomorrow, maybe bring your laptop, bring all your homeworks that